Yes, hi everybody, and thank you to let me talk here today. So I would like to present to you part of my work during my PhD thesis, and my PhD advisors were Grégoire Allaire and Olivier Pons. So we will focus here on a very typical kind of structures that we want to optimize, namely structures which feature a lot of microscopic holes. So I don't want to give too much details, and I guess everyone is convinced now that putting a lot of holes in a structure, it's good for the compliance, thanks to the talk to Jeroen. So we want to put holes, and just to be sure that everyone is aware of what we want to do at the end is to print the structures. So not only to have an homogenized solution, but to have a genuine structure that we could at the end print. So I will focus here on linear elasticity problems, and I would like to minimize the compliance of structures. And to do that, I will use a kind of periodic material, namely orthotopic materials. And one challenge with this kind of materials is the orientation of the cells. So the question is, how can we optimize the orientation of the cell in the wall structure, and how can we regularize it? And of course, at the end, how can I interpret this orientation in order to have a genuine structure? So very briefly, because with the talk from this morning and talk to Jeroen, I guess everyone is okay with homogenization theory right now. So the idea is, if we want to parametrize a classical shape with a characteristic function, so with 0 and 1, and if we want to describe a very microscopic holes, we should have a very thin mesh to do this, and so it will be very time consuming. And another problem with such a model, it's that we'll have ill-posed problems, so it's not a good solution. And the idea is so to introduce composite material, so we average the behavior of a little square of material, including all the microscopic holes, and we average it by composite material which have an homogenized Hooke's tensor so we have here a lattice material, so we use only few geometric parameters to describe the geometry of the periodic cells. And I will denote A star, the homogenized tensor, homogenized elasticity tensor. So yeah, we don't really need this one. And so just to remember, but we saw that this morning, we can compute the homogenized elastic center thanks to a cell problem. So we isolate a cell, we compute some elasticity problems with a function named as correctors, and thanks to these correctors, we are able to compute the A star, so the homogenized elasticity law. And so we can do that for different samples of the geometry parameters P, and so we construct an abacus for our lattice material. And so how can we use this in topology optimization? So classically, when we want to make a shape optimization, we have a shape omega, and so we have the equation of the linear elasticity with omega, and we have an objective function which depends on omega. And here we don't have a shape, we only have the geometry parameters P, so I have my lattice material on the wall domain D, and only the geometry parameters will vary in the wall domain D. So everywhere I have D and no omega, and I have my homogenized elastic tensor. And so the minimization problem is now about the geometry parameters. So to compute an optimal structure, we have a three-step process. The first is the homogenization, so we choose a kind of microstructures and we compute the abacus of the A star. And after that we do the optimization of the structure, and at the end we have the dishomogenization process, so the interpretation as a genuine structure of our previous result. So here, exactly as grown, we have used this kind of periodic cell, so it's a square. The geometry parameters will be the size of the hole, and we add an orientation of the cell. So there is some issues with this orientation, because the orientation alpha is non low modulo pi. If I rotate this structure of pi, we have exactly the same. So this means that if we compute an optimal orientation, we can't have a continuous field. What we can do is to use the double of this angle, beta, and the unit vector field B, which is cosinus beta and sinus beta, and this vector field will be continuous because beta is now known as modulo pi. So we will prefer numerically to use this kind of vector field as the orientation alpha for this purpose. And our elasticity tensor A star, so it depends on, oh sorry, it was L1, but now it's M1. So this is the size of the holes and the orientation. We can split this tensor in different parts. So a part where I have my elastic tensor for a given orientation, typically an angle equal to 0, and a rotation tensor, which depends on the orientation alpha. And in fact, this is a rotation operator for the fourth order tensor. And when we compute it, we found that it can be rewritten as another tensor, which depends on B, so on this continuous vector field, and it's affine with respect to B. So we will see after that it's good news. So with this we can do the optimization. So to do that we used a gradient-based algorithm. So we have an initialization and we iterate until the convergence. So we use the gradient algorithm for the geometric parameters. And there is a trick. We use the periodicity formulas for the orientation, because our cells are orthotropic, and so we want to orientate the strong direction of this square with the eigenvectors of the stress. So this is a result from Peterson. So for example, we try this with a bridge, and here are the results. So here you have the density, and you can see that we have density equal to 1 where I have the load and where it's clamped. And I have almost void aware. And here I have a gray material. This means I have really a microstructure and not a black and white structure. Here you have the orientation. So here it's with alpha, so you can interpret it. And another interesting point is here you have L1 and here you have L2. So you can see it's not the same fields. So this means we have rectangular holes and not square holes. So this is interesting to have this freedom to add some anisotropy to our cell. And just to be sure that everyone is convinced that it's interesting to use the orientation of our cells, here it's the previous result with the density, and here it's the same optimization, but I constrain the angle to be equal to 0. So there is no orientation here, and we can see that we have a black and white structure. This means there is no microstructure in this kind of final structure. And so there is no interest to use microstructures. This can be done using level set or SIMP methods. And it's quite worst because we have a compliance of 4, and here we reach a compliance of 3. So it's like a 25% increase. So we have to use the orientation as an optimization parameter. So, okay, we have our homogenized optimal structure, and how can we use this to reach a genuine structure? So here I have the density, and it's like my cells, my periodic cells, are of size epsilon equal to 0. This is the homogenization method. And so at each point M, I know L1 and L2, so the size of the hole, and I know the orientation, so I can draw the cell. And when epsilon is going to 0, I will find my homogenized structure. But the problem occurs when we want to add neighbors, because if I do the same for this other point, we can see that they don't glue them together nicely, because they don't have exactly the same orientation. And so if I want to build this kind of structure, sorry, it won't be okay. So we have to fill this gap between the two neighbors, and the idea we propose is to distort slightly the cells in order to glue them cleanly. So the idea is we have a regular grid corresponding to our periodic cells. We have a direction field here, and here is what we want to reach. So we want to distort this grid according to this direction field. And so to do that, as Jeroen said before, we use a diffeomorphism. And what we say is, okay, I want a diffeomorphism whose gradient is aligned with my orientation vector fields. So here I have the rotation of the vector, the unit vector fields of the basis. And since I want to distort my cells, I have to slightly dilate them in some areas and to contract them in some other. So I have this little coefficient, dilatation factor. And it's an important thing to say is that we have the same dilatation factor in the both directions. This means that I want a square to be distorted as a square. This means I want a conformal map and not anything else, because everything I did was with square cells, and if I have some rectangular cells in my final structure, I'm not sure that the homogenized tensor of this rectangular cells is equal to the homogenized tensor of the square cells. So I want to keep square cells. And if I want to write that, I have to fulfill some constraint, because if this is a gradient, this means that its rotational is equal to 0. And so when we develop the equation, we reach this kind of final equation. So the Laplacian of our orientation has to be equal to 0. And if it's not the case, I won't be able to compute a conformal map. So I have to regularize my orientation field. So we have a minimization problem. Here it's a compliance. So with the rotation of the stress, it depends of alpha. And I have a little term of penalization. So this is quite classical. And so I want to minimize this under a constraint, which is I want the Laplacian of alpha to be equal to 0 almost everywhere. And if we remember, I said alpha is not a convenient vector angular field because it's not continuous. So we can rewrite our equation, but with beta and with b. And so this is better, but it's still not enough because beta it's non-modulo pi, so I don't modulo 2 pi. So I would like to have b here and not beta. And so we said, okay, it's not linear, so at each iteration n, we will linearize the previous minimization problem around the current state. And so we say, okay, I have beta n and a little increment. And I can rewrite this also in the constraint. And I have a linearized constraint to say the link between my vector field B and my orientation beta. And we have some other equation to express the gradient of beta according to the vector field B. So now I can inject this in my, my equation here, and my minimization problem is only on the vector field B, and the same for the constraint. So I can solve it at each iteration and regularize my orientation with this. So this was the optimal orientation for the bridge case, and we can see that in some areas where the density is almost equal to 0, that it's not very clean, and so we want to clean this. And we can see also here we have not a well orientation, and so we use the previous algorithm to regularize it, and so in, I don't remember, it's 10 or 20 iteration, we reach this regularized orientation. So now it's very clean everywhere. And in the other area, I don't really change my orientation. So it doesn't, it's not a problem for the performance of my optimized structure. So we have a regularized orientation, so we could compute the diffeomorphism, but we still have a little problem, which is the fact that the angle alpha is known up to its the vector field corresponding to alpha is known up to its sign. So if we are looking here, we have some arrows that are going up and some that are going down. So it's okay for the material, but it's not okay if I want to compute the diffeomorphism from here. So we know that we can orientate currently these arrows in the whole domain. So I can choose this kind of orientation or this kind of orientation, for example. And for both, I can compute a diffeomorphism. So I have two copies of my domain D, when the orientation of the arrows are the same up to the sign. And so my diffeomorphism are the same, the gradient of my diffeomorphism are the same up to its sign. And since I'm only interested by the gradient, I can impose to have the same on the diffeomorphism. I just have to change a constant. So this is how numerically we can deal with the discontinuity orientation problem. So numerically, we don't want to orientate currently on the whole domain D. We will see further that it has some interest for other issues. So here it's a mesh with some unit vector field. So it's P1, I know on each vertex. And the idea is, okay, I could have this arrow or I could have the opposite one. So I say I could have both, and now I use a discontinuous P1 element. And so on each elements of my mesh, I choose the current orientation. This is very easy because I have only 3 vectors to orientate locally. And at the end, I say, okay, here is the same orientation as the one I had before. So I said it's plus, and here I change the sign of the previous sign. So I say I have minus. And the idea is here I use this as a part of this domain D. And for example, no, this triangle is a part of this copy of D. So I can compute phi plus and phi minus together, and just by saying on each vertex that he has to be continuous up to its sign. And so at the end, it's what we can compute for the diffeomorphism in the bridge case. So it's the absolute value of the diffeomorphism, and the isolines of this diffeomorphism are aligned with the orientation vector field. So in particular in this area we can see it fits very well. And so when we have this diffeomorphism, we want to proceed to the projection of our structures. So in homogenization theory we have like two sets of coordinates. One is the macroscopic ones, it's y, it's where I am in my cell, and the other one is x, the microscopic, so it's where I am in my domain D. And if we want to describe our cells, only the periodicity cell, here we can use this kind of level set function. So I won't go into the details, but it's only these two cosinus. And so here it's when I am in the periodicity cell, and now I want to be in the macroscopic domain. So we can use this very classical change of coordinates. And here I have now x1 and x2, which are the macroscopic coordinates, and it depends on epsilon, the size of the cells that I want to dishomogenize. And here, so we have x1 and x2, but I want to use my diffeomorphism, so I only have to change here for phi1 and phi2. And as we computed the diffeomorphism only with the orientation vector field, we can here compute this for several values of epsilon, and it's not really time consuming. So we can generate a lot of structures very easily. So here's you have the size of the periodicity cell during the dishomogenization, and when epsilon is going to 0, the size of the cell is going to 0. So we are going to the gray optimized structure. And we want to check if our approach it's good for optimization structures. So here we computed the compliance of this kind of structures for several values of the size of the periodicity cell. So when we are here, we are close to the homogenized solution. And so here you have the volume. And because of the dishomogenization process, we are not sure to have exactly the targeted volume, but we are quite close. And here you have the compliance of these structures. So the dashed line here is the optimal compliance of the optimized and homogenized structure. So we can't go under this value. And here we have the value of another structure which is obtained by the SIMP method. So it doesn't feature any microstructure. It's only a black and white structure. And so we are quite happy because our structures dishomogenized are better than a genuine structure without microstructure. And we are going close to the optimal value, because here you can see that we have a little less volume than what we want. So if we had exactly the same, this point will be a bit down. Okay. So just very quickly, I present this method for a kind of microstructures, which is a square with a rectangular hole. But obviously, we can use this method for other kind of periodicity cells. So if we have a level set function to describe it, so for example, here we know a level set to say if it's negative, if I'm in the material, and if it's positive, I'm in void. We can use this one to build other genuine structure with other periodicity cell. So the method is not restrained to the square cells. And another point is that I said it's good when alpha is known modulo pi, but it's also okay if my orientation of the cell is known to another angle. So for example, if we only have a square, with rectangular, with square holes. I could know this with modulo pi, so modulo pi over 2. So here you have an orientation vector field and a discontinuities of pi over 2. And here I have the isoline of the diffeomorphism phi1, and here for phi2, and you can see that we have the discontinuities because of this discontinuities here. But when I put the balls together, I can reconstruct something that is very continuous. So the idea to do that is the same as previously. Previously we said we have D, and we could have D plus and D minus. And if now I'm using with modulo pi over 2, I could have something like this orientation, a copy of D with this orientation, and this orientation. So I have 4 copies for each covariant orientation of this angle. And so I have phi1, phi2, phi3, and phi4. They are known up to, there is some constraint between them, like we had before phi plus equal to minus phi minus. So it's something which is quite the same in this case. And we can compute, for example, for an element of my mesh here, an element of my mesh here, and everything. And so it's also working for triangle tessellation. So I want to be very quick on this part, because it will be the main topic of the talk of Olivier tomorrow. So I said I want a diffeomorphism which is not given by a gradient, but what I didn't say is I'm not allowed to write this in all cases. It's only possible if my domain D is simply connected. So if I have holes in my domain, I can't find a diffeomorphism which is given by this gradient. So we have to find another solution. So if I'm considering this kind of hole domain, the idea is, okay, I have a near-rotational vector field V on this domain, but it's not simply connected, no problem. I connect the hole to the exterior of the domain, so the new domain is now well connected, and I can compute a diffeomorphism on this new domain. And we wonder what happened along the crack, and we can prove that along the crack, the jump of the diffeomorphism is in fact constant all along the crack. And so we can introduce some correction functions that are defined modulo 1. And so we can add this kind of function to glue the diffeomorphism nicely around this crack. And so numerically, it's just a new minimization problem. So when I have no hole, I could rate this, so I can minimize this kind of problem. And when I have holes, I can do the same equation, but with the correction function. And so here I have my correction function, and here the C coefficient, it's in fact the value of the jump of the diffeomorphism along the crack. And so I have a new minimization problem on my diffeomorphism, but also on this coefficient. So we can solve this. I don't give too much details, but you will have them tomorrow. And so if I want to deshomogenize a wheel, for example, with this orientation, if I do this with my previous methods without using the correction function, here it's the grid I can reach, so it's very bad. And if now I add the correction function, it's the kind of general structure I reach. So it's very nice, and it's well connected. So we don't have here, I have my crack, but I guess no one see a crack here, so I don't see it. And this kind of methods can be used for other purposes. So, as Jaren said, sometimes we can have some singularity in our orientation vector field. It means that on this point, I'm not able to compute a coherent vector field, unit vector field, because the vector field is turning around pi, is turning about an angle of pi around this point, and here minus pi. So here we have issues, and we said, okay, let's go as this point were not in our domain D, so we put a little hole here, and we use the previous method. And we have sometimes this singularity, so here you have an electrical mass test case, and here is the orientation, and you can see that here, 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 and here you have singularity. So we have 4 singularities in this orientation vector field, but we can use the method to deshomogenize it. So here is a distorted grid, and you can see we have a singularity very clearly here because you have 6 squares connected by the same vertex. So this can't happen in a regular grid. And at the end, we can project with geometric parameters. And you can see that the singularity in our vector field has a mechanical, how do you say? It's important for mechanical purpose because this little part is acting as a mechanism to hold together these 3 set of bars. So if we don't use this one, we have to change a lot the orientation in the whole domain D. So if we want to erase singularities from the domain. And so it could be used for other applications. So if we want to tile a domain, for example, we want to print something and we don't want to fill the structure, but we want to partly fill it, we can use this. So what we want is to have a clean orientation of the square along the border. So this is working, and we have here 4 singularities and here 4 other. And it's also working when the orientation is known modulo pi over 2, so like this one. So the orientation is given by the normal to the frontier, but you can see here it's clear. I can have my my square cells which follow well the border. So we want to print structures. So a very big challenge is how can we do with 3D structures. So for the 3D case, I use this kind of cells. So it's a square with holes which are drilling face to face. We choose this one because from an application point of view, if it's printed with metallic powder printers, we could evacuate the powder, so there won't be powder trapped into the final structure. So we know that it's not the optimal one, but we choose this one to address this constraint. So we use a cantilever to test our method. Oh, sorry, I was too quick. The challenge in 3D is always the orientation. So here we use 3 orthogonal unit vectors to represent the orientation. So we can't use only one angle as in 2D. So we have to use more complex model. And we choose this one because it would be easier for the dishomogenization process. And as previously, these vectors, it could be this one or minus this one. It doesn't change here the cell. So we still have this sign problem for the continuity of the vector field in the whole domain. So we can compute the optimized orientation, and as previously, we want to regularize it. So let me show you some. Okay. We want to regularize this orientation as previously, and we don't want to change it a lot, so we only want to change this in some areas where it's not. Here you can see that at the beginning, sorry. At the beginning, the orientation in this part is quite messy, and here it's the same, so we want to regularize it to have something clean, and at the end we have something better. Okay, you can see that it's now it's clear here. So it's working, and the idea here it's quite the same as in 2D. We want to regularize in order to have a clean gradient, but we can't do this as previously because we don't have only one orientation. So the idea is to optimize, to regularize, sorry, a matrix whose eigenvectors are given by the orientation vector omega I, and the eigenvalues are 1, -1, and 0. And doing this and some long change of parameters, we can reach something that is quite interesting to numerically implement, to be numerically implemented. It's not exact, but in fact it's working pretty well. So if you are interested, we can discuss about this, but it would be very long to explain it into details here. So when we have our regularized orientation, we want to compute a diffeomorphism as previously. The problem is that in 3D, if we are considering conformal maps, we will consider very few transformation, so mainly movements of a rigid body and some tricky other one, so it's not enough. And we have to relax this constraint. We can't still constrain this. So we can try and see what will happen, but we know that a cube won't be distorted as a cube anymore. So I want a diffeomorphism whose gradient is aligned with the orientation vector field, and I still have a dilatation factor, but now you can see that it's Ri, so R is not the same in the whole direction, it depends on each direction. So we have two minimization problems. The first, to find the dilatation factor in each direction, so we can compute this very easily. And when we have this dilatation factor, we can compute the diffeomorphism as a minimization problem. And for the issues of sign on the vector field, we use exactly the same trick as in 2D. So we have like two copies of our working domain, and we compute a phi plus and a phi minus on the both copies. And so here you can see the isoplanes of phi1, phi2, and phi3. So I know you can be sure it's a good orientation, but yes, it is. Please just trust me. I can't show you the orientation in 2D, the 3D orientation in 2D. It was not nice pictures. So I have my isoplanes, and now I want to build my periodic cells. So the periodic cube can be constructed by some intersection and union of the isoplanes of the diffeomorphism. And here are some results for the cantilever. So with epsilon going to 0, and you can see that we have bars that are not straight; they are light curved because they are following the orientation. And to compare, you can compare here the 3D model and here a printed structure, so it's the same. So we are able to print this kind of structures with plastic method, and pretty sure that we could do the same with metallic border too. And to finish, I would like to speak about the geometric constraints. So everything I told about, it was about homogenization structures. So I know the final border of my structures only when I did the dishomogenization process. So I can't impose with homogenization geometric constraint on my structure because I don't know the shape. And there is a method to shape optimization where we know exactly the border. It's with the level set method. So we want to couple this both method in order to know the external border of my shape, and so to be able to impose some constraint. So we are now looking at shape omega, and inside of the shape omega I will have my homogenized material. So very quickly how the level set method is working. So I have a shape which is described by a level set function, so the border is given by the zero of the function. And thanks to the derivative of the objective function, we can compute a gradient all along the border of my shape, and we can after that transport the previous shape with this vectors, and we have a new shape, and we can iterate until convergence. So we are doing this now. My objective function is still the compliance, but it's now on the shape omega and no longer on the wall domain D. And I also have a volume penalization because I don't want to have a volume constraint at all iteration. So here is the derivative of my objective function with respect to omega. So it's quite big, but in fact we are able to compute all of this equation, so we can put that in our algorithm. And the idea is we initialize the structure and we iterate, and so we have one iteration with the shape and one iteration where it's the homogenization method. It's important to understand that when I do the level set method, I don't only change the external border of the shape. I also have to smartly transport the homogenized material of my shape to the new one. So this is why here I have quite a huge equation. It's because I want to compute a transport inside of the shape. And so we can use this algorithm for a cantilever. So here it's not, here it's the real shape omega. So here I have really void and not almost void. And here it's where my homogenized material is. So we can dishomogenize this kind of structure. And we can find here quite the same structure that's without the level set. And the same for the shape. So we found here the same structure, so it's good because it means that if we don't have any geometric constraint, our previous method is also working. Both are conducting to the same result. So now we can try this with a geometric constraint. So for example, we want to impose to have a crust or a coat all along the shape. So I defined a domain where the crust has to be, so it's I can describe it with a given high, and I add my penalization term to say, okay, I want that my density of material is almost equal to 1 in this domain. So I add this term to my objective function, and we can use the same algorithm as previously. So here is the cantilever with two different sides of the crust, and we can see that here, okay, I have exactly a density equal to 1, and inside I still have gray material, and the size of the crust is well respected. And when we dishomogenize the previous structures, this is what we can reach. So the final structures are really clean. We don't need some post-process to clean the final structures. And the cross here is on the right size. So here it's larger than this one. Yeah, so I will conclude here. So if you have any question, it will be my pleasure to answer it. Thank you for your attention.
So just have two very small questions. One is close to slide 10 or so, you showed an example of the
Slide 10?
Yeah, I think it was nearby slide 10. You had an example of dishomogenization of the bridge. If you now continue a little. Yeah, and
oh.
Maybe a little further.
It was 10?
Sorry, I thought it was 10. Oh yeah, that one was.
This one? Okay.
Okay, I'm sorry.
No, it's okay.
Mathematicians can't count, as you know. So I was wondering how the bottom structures come about with the. So it seems that at the top,
yeah,
your microstructure says, well, you just have a laminate, just rank. What was it? Rank 1 laminate or rank 0 laminate? I don't know. So just horizontal stresses, and it's not connected at all vertically.
For which one? For this one?
No, the bottom two.
This one?
Yeah, exactly. And there, the top line.
Oh, here.
Yeah, are completely disconnected.
Yes. Okay, we have. There is two explanations that we can have. In fact, we don't have real void here. So sometimes we could have very tiny perpendicular bars here, but we clean them during the homogenization because we won't be able to print them. So we have this kind of final structure, but for the homogenized point of view, yes, they are optimal, but we dishomogenize here, so thin bars are no longer active.
And the second thing is more or less a comment. So in computer graphics, it's a standard problem given a frame so a frame that varies locally,
yeah,
to find a global coordinate system up to certain singularities that fits that frame. Are you aware of that literature?
I know, but the mesh problems they have with some manifolds that they want to tile with quad mesh, and so it's. I guess your question is related to this kind of slide, yeah. So, what exactly is your question?
Well, I just wanted to know whether you're familiar with those.
Yes, I know, and they have other methods, and quite of them are similar because sometimes they say, okay, we have a structure and we are not able to tile it with quad, so we can compute some points where we have singularity, and so we will cut the domain into subdomains, and in these subdomains there is no singularity, so we can have quad, and by the hand they can glue the two connected subdomains together to be sure that the mesh is clean.
Right. So what's the difference to this method? So is it that here the singularities are somehow given from the homogenization, whereas they have to pick the singularities by themselves?
Sorry?
So,
so it was too fast.
So what's the difference between?
The difference is mainly that we don't have to cut the subdomain into other. We cut the subdomains along cracks, and so we want to glue properly this, so we have the same ID, but here it's all automatic. We don't have to change a little by hand the angles. The continuity along the crack is ensured by the coefficient C in front of, so it's all automatic. In fact, I give the orientation vector field to the algorithm, and it found the singularities, the crack, the singularity function, and so the diffeomorphism. So there is nothing else to do.
Their code does as well, right?
Mm-hmm.
But that's what their code does as well, right?
Yes, but in their code, they could. Okay, they can change a little value to be sure it's connected. And here I want to be sure it's always smooth, because I could have, the crack could be along a bar, but it could be also a zigzag. And so I want to be sure it's always working. So it's slightly the same idea, but I'm pretty sure Olivier will be will give more details tomorrow. It's your job.
Yeah. So you showed that you can on the blackboard that if you have up to modulo pi/2, for example, you make 4 manifolds and you pick the vectors from that, right?
Yes and no. In fact, I use a manifold which is the reunion of 4 copies of this domain D, and so I don't really compute a diffeomorphism for each copy. I never have to do that. I just use this trick to compute on one mesh the diffeomorphism.
Then I have a subsequent question. So wouldn't it be possible to use the orientations from the stress in 3D, because they are smooth up to pi/2, and you make 6 copies from which you align the vector?
In fact, in 3D, we use the stress, the eigenvectors of the stress to have the orientation vector fields. And since we are not able to have a conformal map, we compute separately the 3 components of the diffeomorphism. And so I only have 1 vector field at each time. So for each phi1, phi2, and phi3, for all of them, I only have 2 copies of D up to the sign. I don't have to compute current orientation for the 3 vectors at the same time. I only 1. Yeah.
It could be maybe another approach, or is it possible, do you think?
I'm not sure it will be improve anything, because we don't use the 3 vectors at the same time to compute the diffeomorphism.
Something which I didn't quite understand in this passage or generalization from the 2D dehomogenization to the 3D dehomogenization.
Yeah.
So my understanding is that you're given this kind of rotation valued field, and now you want to construct a diffeomorphism.
Yeah.
And the way you did it, as you said, I mean, the Ri, the stretching factor, depends on the direction, right?
Yes.
But that means that something which was cubic in the kind of original homogenization problem now suddenly becomes rectangular.
It could be slightly distorted as a rectangle, yes, because there is no conformal map.
You say slightly?
Because here we can, when we compute the dilatation factor, we have only the gradient of this dilatation factor in two directions. So in the third one, we can penalize it. And here it's a gradient, so I also can penalize the value. So if I have a dilatation factor, I can impose to be very small for all of them. And so it's only the gradient I have here. So it's the same up to a constant. If I have here Ri or Ri plus C, it would be the same. So when I do this, I want them to be, it's like to choose constant such that it minimizes the difference between the 3 dilatation factors.
Yeah, but I mean, it's a question about integrability.
Yes, I can't be sure it will be.
Ri is equal to 1 or very close to 1.
Yes, it could be. But we are trying our best to not have too much dilatation in one direction, but we can't impose that. It's
in general, there will, and that changes the problem. Then, in some sense,
yes, it will change the problem. Yes. So, in fact, what we could do is to say, okay, I'm not using this cube exactly, but this cube and 2 other parameters, which are the dilatation factors in the both directions. And so we will have now 5 geometric parameters, and we could use that, but it also will change here the computation of the diffeomorphism, because we could have here Ri, but also the elongation that was the geometric parameters.
So is it possible to kind of completely make it consistent by choosing a suitable microscopic model?
We didn't do it, but we thought about it, and maybe one day. I guess it's possible, but I don't do it.
To answer your question, yes, I think it's possible, but it's a lot more complicated because in the 2D case, in order to be consistent, the only constraint for our map to be a conformal map is that the lapation of the angle alpha is equal to 0. So it's a linear constraint. And then if you allow rectangular cells, or same in 3D, then the constraints, you have a constraint on the dilatation factors are 1, are 2, are 3, and on the angle 2, and all are coupled together, and it's nonlinear.
Mm-hmm.
So I think it should be possible, but definitely it will be probably more difficult.
Mm-hmm. Can I ask a
Yeah.
question? So I mean, from the very beginning, when you make this ansatz, probably the problem, after homogenization is not closed in the sense that in principle the optimizers would still form a microstructure, would still like to form a microstructure within this set of parameters.
I'm sorry.
To put it more abstract, but perhaps that's I'm missing a simple point. You look at this homogenized matrix A star as it
Yes.
depends on the set of parameters P that defines a certain set in matrix space.
Yes.
That's probably not closed under homogenization.
Yeah.
So there is. What tells you that you have chosen a good set? Why don't you run into this problem that even though you've used homogenization, the numerical algorithm produces again microstructure? Are you lucky that it doesn't, or what, why?
No, I didn't. You mean that we could have? I'm pretty sure I didn't understand. Yeah.
I would say the other way around, if I can help her at that time. She gave an example where she was not doing any rotation.
Yeah.
So she was using a composite, but without rotation,
Yes.
and then
Yes.
what you get is a black and white design. That is,
Yeah.
composites are not optimal in this case.
Yeah.
Yeah.
So you are lucky when you see that composites are indeed used. Of course, the problem is not well posed, but if they are not optimal, they will be eliminated from the final solution. And that's exactly what happened
It's
here.
here.
Right. So in a certain sense, in the right picture, it's clear that you haven't kind of gone to the. You're very far from a model that's closed.
Yes.
And in the left picture, you're a little bit closer, but you're not. It's still.
I'm not sure.
Oh, no. We're not sure. This is not the optimal value of the compliance. We could have a more optimal value with laminates.
Yeah, but that's still. So the question I'm asking might be simpler in the sense that your set of matrices which you reach, is it almost G closed? I don't know whether.
No.
It's not.
No.
So then my question is why don't you see that when you do numerical simulations? Why don't you see that the algorithms, when you try to minimize, wants to go
It's
to
not very far. Numerically, it's not very far.
Okay.
But it's
So
no
it's
reason.
almost, it's almost closed. Yes.
Almost
Yeah,
close.
almost in the numerical sense.
Close to being.
And you have some regularization over the parameters.
Yeah.
And
And the M1 and M2.
Slight small regularization that do prevent acting like
Okay. More questions?
patterns.
So, thank you very much.